we're going to talk about linear momentum again, except now we're going to introduce this idea of elastic collisions. But first, a refresher. When's momentum conserved? Whenever your external forces are zero, because forces cause external forces, that is, cause a change in momentum. When can you apply it? All the time. Any collision. All this works. Particularly useful in collisions. When can you apply conservation of energy? All the time. Energy always goes somewhere. That's the best part about energy. But when's it useful? It's only useful in isolated systems where you know where all the energy is going. And we're going to look at a case called an elastic collision where you do know where all the energy goes. You're not going to worry about smashing blocks or making funny noises. You're going to be able to track each piece of the energy. As we just mentioned, no energy is going to be lost to heat or sound. You can track all of the energy, which gives you another playing field to work with. Because now not only do we have conservation of momentum, we're also going to get conservation of energy. Let's see how this is useful. So here I've got a little block that's hitting a big block. And if you have a little block that hits a big block, it'll bounce back. And then the big block will go forward a little bit. Is momentum conserved? Well, yes, it's a collision. There's no external forces. So I'll start there. I'll start with momentum conservation. The little block has some velocity, and at the end, the little block has momentum, and so does the big block. But this leads to a problem that I have two unknowns. I don't know both final velocities. But, can I track the energy? Yes, thank goodness. All right, so I know that the total change in energy is zero. I'm not worried about the blocks deforming. I'm not worried about breaking holes. I'm not worried about funny noises. I know where all the energy went. Initially, I have kinetic energy from block A, and at the end, they both have kinetic energy. Well, great, this gives me that second equation. Two equations, two unknowns. We can totally do this one. So we have momentum. This is momentum equation that we've already gotten. And I can solve for VAF, the final velocity of block A, but it's in terms of this block B. So now I have energy conservation. Here I divided by the 1/2, just to make it look a little nicer. And we will substitute our expression that I got from the momentum equation into the energy equation. Well, now it's just super fun algebra. So we'll expand that middle term. Oh, well, that's nice. The first term went away. And then we'll just keep on going. So we'll keep on trucking. Please do this yourself so that you can verify as it goes, or slow down, try a step, and double check my work. The VBs go away. Oh, wait. And now I just have this nice expression for the velocity of block B. I know the initial velocity of A. I know the two masses. That's great. So then I can plug that back into my initial expression and get VA final and VB final. Not too shabby. Now let's try a different example. So here I've got VA. It's going to squish into block B. And I want to know what's the maximum distance that this spring is going to get compressed. So the velocities of blocks compare. How do they compare when the spring is compressed to maximum distance? They're going to be equal to each other because when it's compressed the maximum distance, those two blocks are going to be sliding together. Is momentum conserved? Yes, always. So I know the initial momentum and the final momentum are going to be equal to one another. Initially, just the block A is moving. Finally, both blocks are moving at the same speed. So I now have an expression for the final velocity. Good. That's nice. Can we track all the energy? Yes. All right, change in energy 0. So what do I have at the beginning? Beginning, I just have kinetic energy from block A. At the end, I've got the kinetic energy of both. This spring energy. Okay. So what we're going to do, we're going to substitute in that velocity that we've got. If you see the pattern, so we use conservation of momentum. So this is from conservation of momentum. We find the velocity, we plug it back into the energy equation when energy is conserved. Two variables, two unknowns. I'm going to make the 1/2 divide out. And then I just get this expression for change in position. And that's how it works. So when you have conservation of energy, meaning you can track all of the energy terms, and there's no external forces, you can use conservation of momentum together. Works out all right. I hope this helps. Please ask any questions, and I will talk to you later. See you in class.